In the last video, we talked about the multivariate Gaussian distribution and saw some examples of the sorts of distributions you can model as you vary the parameters mu and sigma. In this video, let's take those ideas and apply them to develop a different anomaly detection algorithm. To recap, the multivariate Gaussian distribution or the multivariate normal distribution has two parameters mu and sigma, where mu is an n-dimensional vector and sigma, the covariance matrix, is an n by n matrix. And here's the formula for the probability of x as parameterized by mu and sigma. And as you vary mu and sigma, you can get a range of different distributions. Like, these are three examples of the ones that we saw in the previous video. So let's talk about the parameter fitting or the parameter estimation problem. The question, as usual, is if I have a set of examples x1 through xm, and here each of these examples is an n-dimensional vector, and I think my examples come from a multivariate Gaussian distribution, how do I try to estimate my parameters mu and sigma? Well, the standard formulas for estimating them is you set mu to be just the average of your training examples, and you set sigma to be equal to this. And this is actually just like the sigma that we had written out when we were using the PCA, or the principal components analysis algorithm. So you just plug in these two formulas, and this would give you your estimated parameter mu and your estimated parameter sigma. So given the data set, here's how you estimate mu and sigma. Let's take this method and just plug it into an anomaly detection algorithm. So how do we put all this together to develop an anomaly detection algorithm? Here's what we do. First, we take our training set and we fit the model, we fit P of x by setting mu and sigma as described on the previous slide. Next, when you're given a new example x, so if you're given a test example, let's take an earlier example. Let's say I have a new example out here, and that's my test example. Given the new example x, what we're going to do is compute P of x using this formula for the multivariate Gaussian distribution. And then if P of x is very small, then we flag it as an anomaly, whereas if P of x is greater than that parameter epsilon, then we don't flag it as an anomaly. So it turns out if we were to fit a multivariate Gaussian distribution to this data set, to just the red crosses, right, not the green example, you end up with a Gaussian distribution that places loss of probability in the central region, slightly less probability here, slightly less probability here, slightly less probability here, and very low probability at the point that's way out here. And so if you apply the multivariate Gaussian distribution to this example, it will actually correctly flag that example as an anomaly. Finally, it's worth saying a few words about what is the relationship between the multivariate Gaussian distribution model and the original model, where we were modeling P of x as a product of this P of x1, P of x2, up to P of xn. It turns out that you can prove mathematically, I'm not going to do the proof here, but you can prove mathematically that there's a relationship between the multivariate Gaussian model and this original one. And in particular, it turns out that the original model corresponds to multivariate Gaussians where the contours of the Gaussian are always axis aligned. Right? So all three of these are examples of Gaussian distributions that you can fit using the original model. It turns out that that corresponds to multivariate Gaussian where the ellipses here, the contours of this distribution. It turns out that this model actually corresponds to a special case of a multivariate Gaussian distribution. And in particular, the special case is defined by constraining the distribution of P of x, the multivariate Gaussian distribution of P of x, so that the contours of the probability density function, of the probability distribution function, are axis aligned. And so you can get a P of x with a multivariate Gaussian that looks like this, or like this, or like this. And you notice that in all three of these examples, these ellipses, or these ovals that I'm drawing, have their axes aligned with the x1, x2 axes. And what we do not have is a set of contours that are at at an angle, right? And this corresponded to examples where sigma is equal to 1, 1, 0.8, 0.8, let's say, with non-zero elements on the off diagonals. So it turns out that it's possible to show mathematically that this model actually is the same as a multivariate Gaussian distribution, but with a constraint. And the constraint is that the covariance matrix sigma must have zeros on the off-diagonal elements. In particular, the covariance matrix sigma, this thing here, it would be sigma squared 1, sigma squared 2, down to sigma squared n. And then everything on the off-diagonal entries, all of these elements above and below the diagonal of that matrix, all of those are going to be 0. And in fact, if you take these values of sigma, sigma squared 1, sigma squared 2, down to sigma squared n, and plug them into here, and plug them into this covariance matrix, then the two models are actually identical. That is, this new model using the multivariate Gaussian distribution corresponds exactly to the old model if the covariance matrix sigma has only 0 elements off the diagonals. And in pictures, that corresponds to having Gaussian distributions where the contours of this distribution function are axis aligned, so you aren't allowed to model the correlations between the different features. So in that sense, the original model is actually a special case of this multivariate Gaussian model. So when would you use each of these two models? So when would you use the original model, and when would you use the multivariate Gaussian model? The original model is probably used somewhat more often, and whereas the multivariate Gaussian distribution is used somewhat less, but it has the advantage of being able to capture correlations between features. So suppose you want to capture anomalies where you have different features, say where features x1, x2 take on unusual combinations of values. So in the earlier example, we had that example where the anomaly was with the CPU load and the memory use taking on unusual combinations of values. If you want to use the original model to capture that, then what you need to do is create an extra feature, such as x3 equals x1 over x2, equals maybe the CPU load divided by the memory use or something. And you need to create extra features if there's unusual combinations of values, where x1 and x2 take on an unusual combination of values, even though x1 by itself and x2 by itself looks like it's taking a perfectly normal value. But if you're willing to spend the time to manually create an extra feature like this, then the original model will work fine. Whereas in contrast, the multivariate Gaussian model can automatically capture correlations between different features. But the original model has some other, maybe more significant advantages too. And one huge advantage of the original model is that it is computationally cheaper. And another view on this is that it scales better to very large values of n, to very large numbers of features. And so even if n were, say, 10,000, or even if n were equal to 100,000, the original model will usually work just fine. Whereas in contrast, for the multivariate Gaussian model, notice here, for example, that we need to compute the inverse of the matrix sigma, where sigma is an n by n matrix. And so computing sigma, if sigma is a 100,000 by 100,000 matrix, that's going to be very computationally expensive. And so the multivariate Gaussian model scales less well to large values of n. And finally, for the original model, it turns out to work okay even if you have a relatively small training set. This is a small unlabeled example that we use to model P of x, of course. This just works fine even if m is maybe 50, 100, it works fine. Whereas for the multivariate Gaussian, it is sort of a mathematical property of the algorithm that you must have m greater than n, so that the number of examples is greater than the number of features you have. And there's a mathematical property of the way we estimate the parameters that if this is not true, so if m is less than or equal to n, then this matrix isn't even invertible. That is, this matrix is singular, and so you can't even use the multivariate Gaussian model unless you make some changes to it. But typical rule of thumb that I use is, I would use the multivariate Gaussian model only if m is much greater than n. So this is sort of the narrow mathematical requirement, but in practice I would use the multivariate Gaussian model only if m were quite a bit bigger than n. So if m were greater than or equal to 10 times n, let's say, might be a reasonable rule of thumb. And if it doesn't satisfy this, then the multivariate Gaussian model has a lot of parameters, right? So this covariance matrix sigma is an n by n matrix, so it has roughly n squared parameters. Because it's a symmetric matrix, it's actually closer to n squared over 2 parameters, but this is a lot of parameters, and so you need to make sure that you have a fairly large value for m. Make sure you have enough data to fit all these parameters. And m greater than or equal to 10n would be a reasonable rule of thumb to make sure that you can estimate this covariance matrix sigma reasonably well. So in practice, the original model shown on the left that is used more often, and if you suspect that you need to capture correlations between features, what people will often do is just manually design extra features like these to capture specific unusual combinations of values. But in problems where you have a very large training set where m is very large and n is not too large, then the multivariate Gaussian model is well worth considering and may work better as well, and can save you from having to spend the time to manually create extra features in case the anomalies turn out to be captured by unusual combinations of values of the features. Finally, I just want to briefly mention one somewhat technical property, but if you fit a multivariate Gaussian model and if you find that the covariance matrix sigma is singular, or you find it is non-invertible, there are usually 2 cases for this. One is if it's failing to satisfy this m greater than n condition, and the second case is if you have redundant features. So by redundant features, I mean if you have 2 features that are same, somehow you accidentally made 2 copies of the feature, so maybe x1 is just equal to x2. Or if you have redundant features, and maybe maybe feature x3 is equal to feature x4 plus feature x5. Okay, so if you have highly redundant features like these, where if x3 is equal to x4 plus x5, well, x3 doesn't contain any extra information, right? You take these 2 other features and you add them together. And if you have this sort of redundant features, duplicated features, or this sort of features, then sigma may be non-invertible. And so there's a debugging step. This should very rarely happen, so you probably won't run into this. It's very unlikely you have to worry about this. But in case you implement a multivariate Gaussian model and you find that sigma is non-invertible, what I would do is first make sure that m is quite a bit bigger than n. And if it is, then the second thing I do is just check for redundant features. And so if you have 2 features that are equal, just get rid of one of them. Or if you have redundant features like these, x3 equals x plus x5, just get rid of the redundant feature, and then it should work fine again. As an aside, for those of you that are experts in linear algebra, by redundant features, what I mean is the formal term is features that are linearly dependent. But in practice, what that really means is one of these problems tripping up the algorithm, and if you just make your features non-redundant, that should solve the problem of sigma being non-invertible. But once again, the odds of you running into this at all are pretty low, so chances are you can just apply the multivariate Gaussian model without having to worry about sigma being non-invertible, so long as m is greater than or equal to n. So that's it for anomaly detection with the multivariate Gaussian distribution. And if you apply this method, you'll be able to have an anomaly detection algorithm that automatically captures positive and negative correlations between your different features and flags an anomaly if it sees an unusual combination of the values of your features.